All right, hello everyone, and welcome to our last video together. This is it. This is our final video. We've made it. All right, so today we're going to be looking at series, both geometric and arithmetic. All right, and looking at yeah, some series. Okay, so first we're going to define what a series is. All right, then, like I said, we're going to look at the arithmetic series versus geometric series, and then we're going to talk about an infinite geometric series. Arithmetic can't be infinite, so it only works with geometric, and we'll talk about that when we get there. So let's do this. Let's do our last video together. Okay. Oh, let me move my head. Okay, so here we go. All right, let me get my pad, my notepad, my iPad out in front. Oh my gosh, I can't believe it's the last one. All right, focus. Okay, so first off, we need to talk about what is a series. So we have sequences, which is just a string of terms that have some kind of pattern connecting them, right? So some kind of pattern sequence or a patterned list of terms. We call that a sequence. A series is just the sum of the terms in a sequence. So series is when we're adding up all the numbers in a sequence and we're finding the sum, right? That's what addition is, right? When you add things, it's called the sum, right? So the sum of terms in a sequence. The sum of terms in a sequence. That's what a series is. All right, so it's when you're adding up all the terms. Okay, so there's special notation that is used to denote a series, and it looks much scarier than it actually is. This is something called summation notation. All right, summation, right? A sum, and notation, you know what that means, right? It's just how you write something. All right, so to indicate a series, we use this summation notation. All right, so summation notation is used to represent a series. And remember, a series is just the sum of terms of the sequence. So it's all kind of combined. All right, so this is what a summation notation setup would look like. All right, so you use this symbol, which I'm sure you've seen before. You might not know what it is. All right, that weird sideways M, capital E looking thing. This is a summation. All right, it is a capital Greek letter S, I'm guessing. I actually never Googled it, but I'm pretty positive it's probably a Greek capital S. So what we do with this is, so this is the big symbol. Anytime you see this, think sum, think addition. We're adding things, all right? And then there's parts to it. So usually right inside, so like this would be considered like the inside piece. This is where your sequence, your explicit equation for your sequence is going to go. So we use A sub n. All right, so this is our explicit equation. All right, and again, it doesn't matter. It could be a geometric sequence, could be arithmetic sequence, could be quadratic sequence, which we didn't talk about, but those are a thing. There's a ton of different types of sequences. Whatever your sequence is, it goes right here in that summation, like parentheses. All right, on the bottom of the summation, so down here near the bottom, n equals 1. This is the starting term. So this is the term you're going to start on for your sum. Now you don't always have to start with the first term. Maybe you care about adding up terms 10 through 30. So you would, instead of saying n equals 1 at the bottom, you would say n equals 30. Whatever it is, whatever term you want to start with, that's the number that goes on the bottom. All right, so this is your starting term. All right, so whatever term you want to start on in your sequence to start adding up, that's what goes on the bottom. And then what goes on the top is your ending term that you want to stop with. All right, so whatever goes on top, it can be anything, can be infinity. All right, so I'm just going to put infinity because that happens more often than not. All right, so it doesn't matter. Whatever number is at the top, this is the term number that you stop with. All right, so term number you stop adding with. I don't know. That makes sense to me. It's the ending term that you're adding up. All right. So say you wanted to, like I said, say you wanted to add up terms like 10 through 30. then you would do n equals 10 on the bottom, and you would put 30 at the top. All right, so bottom is starting point, top is ending term. And then inside the parentheses, that's your explicit equation. That's it. So that is what we call summation notation. All right. And the reason we use this is because there's a lot of variables in there, right? So you need an explicit equation, you need your starting point, and you need your stopping point. All right. So there really isn't just like a straight way to write this. So that's why we use this summation notation, because it has all the information that we need kind of in a nice, pretty little bundle. I know that the summation symbol looks kind of scary at first, but it is kind of compact when really it's a lot of stuff we're saying there. So the symbol itself represents sum. We have our starting, our ending, and then our equation that we're using to plug in those n values. Okay. So that is, like I said, the summation notation. All right. Now you're going to see the words partial sum a lot in, today's worksheet and, today's notes. You see, if you're already kind of looking, you can see partial sum of arithmetic, partial sum of geometric. A partial sum is when you are just adding part of a sequence, right? So what we have kind of written in that summation notation, this would be an infinite sum. You're starting with the first term and you're adding through infinity. You're going to keep adding up the terms forever and always. So this is what we would call an infinite sum, and we are going to talk about that in a second. But a partial sum is when you pick and choose which parts of a sequence you actually want to add up. All right, so that's what we need by a partial sum. So this is adding up. We'll use a different color here. So this is adding up, how do I want to word this? Adding up a specific section of a sequence, right? Because you're picking and choosing. So we'll do, like, for example, all right, if we have like n equals 3 and then 7 up at the top, all right, and then we have some kind of explicit equation, I don't know, we'll say 2n plus 1. All right, this means that we want to start with the third term, end with the seventh term, and add up those. All right, so this is what's called a partial sum, and we're just gonna do it. All right, so we start by plugging in the n values. All right, so if we're starting with 3, that's going to be the first n that we plug in. So 2 times 3 plus 1. So 2 times 3 plus 1. All right, this is going to give us, so I'm not going to actually write that because that's going to get really big. All right, so 2 times 3 plus 1, so that's 6 plus 1, so 7. All right, this is n when n equals 3. All right. Our fourth term, so now we bump up the n to 4, and we plug in a 4 for n. So 2 times 4 is 8. 8 plus 1 is 9. So this is when n equals 4. All right, we go up to 5. So when n equals 5, 2 times 5 is 10, plus 1 is 11. So that's n equals 5. All right, when n equals 6, you do 2 times 6, which is 12, plus 1, which is 13. So that's n equals 6. All right, and then last one when n equals 7, so 2 times 7 is 14, plus 1 is 15. All right, so and then we stop, right? Once we hit n equals 7, we stop because that is how far we want it to go. So now the sum is when we add up all of these numbers. So we're going to add up 7 plus 9 plus 11, so 7, oops, clear, 7 plus 9 plus 11 plus 13 plus 15. And so our final answer is 55. That is the partial sum of this sequence, right? Starting with term 3, ending with term 7. So that is a partial sum of a sequence. All right, now there are formulas, so you don't have to do this, right? That was kind of tedious, right? I had to like find the third term, find the fourth term, find the fifth term, sixth term, seventh term, blah, blah, and then I had to add them all up. Well, luckily there is an equation for an arithmetic series and for a geometric series where you don't have to find each individual term and then add them up at the end. It'll actually just do it all in one step for you. So it's actually really nice. All right, so our partial sum for our arithmetic series looks like this. All right, I just moved it up a little bit. All right, so for arithmetic series, we have, so S subscript n. So this is our symbol for a series, right? So when we had a sequence, our sum was a sub n. So a series symbol would be s subscript n. All right, equals n, which is our number of terms we're adding up, divided by 2, parentheses, a1, which is the first term, plus a sub n, which is the nth term, close parentheses. All right, so just recap. S sub n, this is the symbol for series. All right. N by itself is the number of terms we are adding. A1 is the first term that we're adding. And then a sub n is the final term that we're adding. All right, now generally, I know I keep saying it's the first term that we're adding, the final term that we're adding, the total number of terms we're adding. Generally, and for you guys in this class, because this is kind of like a condensed version of this unit, it's like sequences and series light, we are always going to be starting with term number 1 as the first term that we're adding the sequence. So we're not going to be doing ones like that example problem where we started at term number 3 and went to term 7. We would always be starting with term 1 and going to whatever term. So n is going to end up being like, you know, if you want to add 50 terms, then n would be 50, right? So it makes it a little bit easier because we will be starting always with the first term. But in general, n would change. Like say you wanted to start with term 4 and end with term 50, then a1 would really be a sub 4 because it's the first term that you're starting with to add. And then if you wanted to start with 4 and end at 50, you wouldn't plug in 50 for n. You would plug in, 46? Because that's how many terms you're actually adding together. So it gets a little bit complicated when you don't start with the first term. But luckily for us, we are always going to be starting with term number 1 for doing our partial sums. Okay. So that is, like I said, the partial sum of an arithmetic series. So that's your formula. All right. For geometric, it's a little bit different because remember, geometric sequence is a little bit different, right? They're not the same formulas. All right. So this is what you would look like for geometric. So it'd still be S sub n because that's like our general, series notation. All right. Equals. And then this one is going to be A1. So like your first term, parentheses, 1 minus r to the power of n all over 1 minus r. And remember, r is your, so we'll just do all this, right? So A1, this is your first term. R is your common ratio. N is the number of terms that you're like adding up, right? So this is number of terms that you're adding. Right down here again, we have R is our common ratio, right? We just have it in here twice, common ratio. All right, so that is your formula for partial sums of geometric series. All right. So it's kind of, they're a little different from each other. They both have common things, right? So we both of them have A1, both of them have like the number of terms, right? You have an N in there somewhere. The differences really come from in your arithmetic series, you have A sub n, which is your final term that you want to kind of add up. Whereas in your geometric series, they use the common ratio. All right, so a little bit of differences, but they do the exact same thing. So both formulas are going to add up the amount of terms we want in a sequence and then give us that final answer. So we don't have to do what we did in that top example by finding each individual term and then adding. That is very tedious and we don't want to do that. All right, now, because geometric sequences can have can diverge, right? So in order for a sequence to diverge, an arithmetic sequence is never going to diverge because you're just adding or subtracting a number over and over again. There's no fractions involved. It's just one number that you're adding or subtracting over and over, and it's just going to keep either making your number grow in the positive direction or grow in the negative direction. So arithmetic sequences are never approaching a single value. So we can't actually find the ultimate sum of an arithmetic series because the numbers are just going to keep getting bigger and bigger, either in the positive direction or the negative direction. So you're just going to have a bigger and bigger and bigger sum. So arithmetic does not have an infinite sum, but because geometric series can actually converge to a specific number, right? Especially if you're multiplying by a fraction over and over and over again, your numbers are just going to keep getting smaller. So even though you're continuously adding when you're doing a series, if you keep adding numbers that are extremely small, it doesn't increase your number by that much. And you can have a geometric series that converges to a single value. And so that's when we have this infinite sum. So in a geometric series, you can eventually add up to one specific number. And so we would say you converge to one value. All right, and it's actually pretty easy to figure out if a geometric sequence is going to have an infinite sum. All right, so here is the check. So what you need to do is look at your geometric sequence, not series, the sequence itself, and you want to find the R value, that common ratio. All right, and the rule is if the absolute value of that common ratio is less than 1, meaning if your common ratio is a fraction smaller than 1. So not just a fraction, right? Because 3/2 is a fraction, but that's not smaller than 1. So you want like 1/2, 1/3, 2/5, something like that, right? So if the absolute value, right, is less than 1, then this is a convergent series. Okay, so that common ratio has to be some number less than 1 absolute value, right? We're not talking about like negative being less than 1. So somewhere between 0 and 1, it's going to be, you're just looking at the number itself, right? Not the negative and positive sign, right? It will be a convergent series. And to find what that series, the infinite sum is, all right, there's a really easy equation. So the limit, right, because when we're talking about converging, we're always talking about limits, right? The limit as n goes to infinity of s sub n, right? S sub n is our series. It equals the first term divided by 1 minus r. That's what you have to do. So you take the first term and you divide it by 1 minus that r value, and that's going to tell you what your sequence is going to approach as you keep adding up the terms in that sequence. So ultimately, what is your infinite sum of your geometric series? Series is when we're adding them together. That's it. Okay, so for examples, we're actually not going to do them in this video today. There's a lot of different example problems that I want to go over, and I think just adding them onto this video is just going to make the video really long, and we're still going to want to go over the problems together anyways. So what I'm saying is for this last video, which I should have done as soon as we started like going back to class, like in person. I should have just done this from the beginning, but I didn't. I figured it out in the very last video, so it is what it is. We're just going to do a few problems from your homework for today's examples. All right, there's a lot of different types that I want to look over with you guys, so doing them in the video, it would just make the video too long. So we are going to go over some problems from the homework now, probably one from each section. All right, that's today's video, and that's the last video of all of the videos. It has been a really fun year with you guys, even though it's been strange. I know it's been strange, and I know that we've all complained, but it has been really fun to kind of do, a new year, right? It's been something completely different from what we've been used to. I've never, made these, videos before, so if they were really bad, I'm sorry, it was my first attempt, right? If they were good, I'm glad you liked them. But yeah, that's our last one. Anyways, it probably means more to me maybe than it means to you because I made it. It's like a really huge project that I feel like I just finished because these do take a lot of time, right? Anyways, it's been great, and I will see see you guys in class. And if you're if you're in class, it's probably really weird to watch this. I hope I cut the video short at this part because I'm just rambling. It has nothing to do with math. But yeah, all right, cool, excellent. Last video. Bye, guys.